around skin or bone, and there's also just error in it because the original X-ray image is so difficult to see. And currently, to do image segmentation, there's two main methods: the convolutional neural network, or CNN, and the UNet, which builds on top of the convolutional neural network. A neural network is just a series of neurons with weights and biases that are adjusted through the training process. And in a convolutional neural network, it adds on a convolutional layer to the start, where it takes each part of an image and applies what is called a kernel, which is just a matrix of numbers that is adjusted through training, and creates what are called feature maps. And so each part of an image will have multiple feature maps, as you can see here. And then these feature maps are used in a neural network to try and classify each pixel as 1 or 0 based on whether or not it is background. The UNet builds off of these basic ideas in the CNN, and it is technically classified as an encoder-decoder network with skip connections. The encoder half, or the left side of this UNet-shaped architecture, it reduces the size of the image and extracts these different feature maps through convolution. And then the right half, where it expands back up, known as the decoder, increases the size of the image back up to the original size of the X-ray, and takes these generalized features from the first half and combines them through skip connections with the original image to keep context and create extremely precise segmentations without having to have a doctor go through and look at each one. And so our hypothesis tried to solve both the problems with bone age and with image segmentation with one model. And we asked the question, can a model with a UNet architecture perform image segmentation without human intervention while still achieving comparable accuracy to current state-of-the-art supervised models? And so the first step was defining what the state-of-the-art model was. And the state-of-the-art model that we used utilized 12,000 X-ray images with 300 annotated images from a radiologist, and used the UNet to learn from that huge data set and achieve scores of above 94%. It also used an ensemble regression method to predict the actual bone age from the segmentations and achieved an error of around 7.4 months on average. And so the data we decided to use comes from the RSNA Pediatric Bone Age Challenge, which is a data set of 14,000 left-hand wrist x-rays, all of different shapes, sizes, intensities, and from different facilities across the world. And we used a very small subset of this huge data set, using only 100 images for the training and 50 for testing, which the model would never look at until it was time to evaluate it. However, there was one problem with the subset of the model of the data that we chose, and that was the distribution of bone ages, which, as you can see, is skewed towards older children with bone ages above 120 months or 10 years, and this will come up later when we're evaluating the model. And for each of the 150 images we used, we utilized pre-processing with claw-head normalization, and also did basic background removal using Python. Claw-head normalization just brightens the actual bone of the image while dimming the skin and the background, so it's easier to look at and easier for a model to distinguish between the different parts. When we're looking at the data, we noticed multiple challenges that have been faced by other people that use the same pediatric bone age set. And that is the expensive or just unavailable annotations that you would need a radiologist to go through and segment pixel by pixel traditionally. There was no standardization across x-rays, as each one looked extremely different from each other. Even if a radiologist took 2 x-rays back to back, they could still have hands in very different positions and with different brightnesses based on how they're taken. Also, as you can see here, this image itself is extremely complex and noisy, and even with a trained human eye, it can be difficult to tell the different parts that are important for bone age, especially the smaller wrist bones that can barely be seen in an x-ray until it is blown up. So this data showed that we required the ability to generalize and adapt quickly from whatever model we chose. And this lined up perfectly with what the UNet has been used for traditionally in the past, and that is for biomedical images and generalizing through the adjustment of hyperparameters through training. UNets also require very little data for training, but 150 images was still rather difficult to use because UNets traditionally still use somewhere in the hundreds of images. And so what we first tried off was to adapt the basic structure of the UNet using a Mumford-Shaw loss functional, which is essentially just a descriptive statistic that compares the original X-ray image to the segmentation that's being produced. And through the learning process, it tries to minimize the loss function. This loss function rewarded pixel boundaries that were decided based off the original image, and it would look at how similar pixels within a boundary are to each other and how different they are from the pixels around them. And so this would end up producing something that looked more like a checkerboard or a black screen, because in a checkerboard, each pixel within the box is extremely similar to itself because they're all black, but they're also very different from the ones surrounding it, which are all white. And so that obviously didn't give us the results that we're looking for. So we moved away from the UNet and tried different traditional unsupervised methods, starting off with the GAN, or Generative Adversarial Network. This is an unsupervised method that tries to fool itself in distinguishing fake X-rays from real, and is usually used for hyper-realistic images, such as creating artwork based off of an artist's style. And here we realized that it would just create X-rays that look almost identical to the original because they already look realistic. And so to try and fake itself out, it would just create the same image. And so that also didn't work. So on more traditional k-means clustering algorithm, which finds similar pixel groups within an image and tries to put them into similar categories. And here, as you can see on the very right-hand side, the top example actually is segmented extremely well with a level of detail that may not actually even be necessary. But on the bottom, it captures a lot of noise and gets fingers that are out of proportion and a lot of the background and just noise that makes the image difficult to deal with. And so by looking at the traditional disadvantages of k-means and the traditional disadvantages of the UNet, we decided to use them in conjunction with each other to hide each other's flaws. And so what we did was we took our original 100 training images, fed them through a pre-processing pipeline that used the claw-head normalization to create our enhanced inputs, and then fed these same images into the k-means clustering algorithm to create what are called pseudo-ground truths, which are imperfect models for what the data should be producing and are what it uses in the learning process to try and predict what its output should look like. But where this differs from a normal algorithm is these ground truths would usually be perfect down to the pixel so that the model knows exactly what it's looking for. And so to use pseudo ground truths is a big jump in the field of image segmentation because it's very rare to see. People use ground truths that may not be perfect and may result in the model learning behaviors that are unwanted. And we decided to go with a dense UNet, which is a type of UNet that expands very quickly the number of features, but is rather shallow, just to avoid overfitting to these ground truths that themselves are not perfect, so we don't want them to learn completely from those. And it produced segmentations that look like that, which are more of a blend of the input and the output, capturing both the good aspects of the original X-ray and the good aspects of the k-means clustering, and then fed this to a support vector regression model that would give us an ultimate bonage. And our proposed segmenter achieved comparable accuracy to state-of-the-art models while using a significantly smaller portion of the data set. In training, we used a 70-30 training validation split to evaluate the model while it was training, and employed a standard loss function of binary cross entropy, and also used early stopping to look at the validation loss to stop the model whenever the validation loss was starting to decrease to avoid overfitting. And as you can see across the bottom, we got pretty satisfactory results where a lot of the X-ray segmentations would preserve a lot of the rather minor details in the wrist while still capturing the important bones and fingers in the image and still not being tricked out by noise or differences in the original image, as it works on both very good high quality X-rays and ones that are more fuzzy and difficult to see with the naked eye. And we did this using only approximately 0.07% of our original data set, while the state-of-the-art model used all 12,000 images, while still achieving a dice score around the state-of-the-art model with 150 annotated images, but is a little bit lower than that with the 300 annotated images. However, our model was not perfect, especially when it comes to predicting the actual bone age compared to the segmentation, because the SVR model suffered from the distribution of bone ages in the dataset, but still achieved comparable and acceptable accuracy given the proposed segmenter and sufficient data. We used the grid search CV, which searches for the optimal parameters for a machine learning algorithm, and settled on a radial basis function kernel and a degree of 3 for the SVR model. And in the top image, it does an extremely good job of predicting the bone age from a segmentation that does reflect what a radiologist would also produce, and ends up being only around 2 months off. And on the bottom, however, with a child's hand that has much more skin and distractions, it does extremely poorly, producing something that barely looks like a hand and having a prediction of 109 months when it was actually 12. And this connects back to the distribution of bone ages in our data set, where we had very, very little data on the lower end of the spectrum between 1 and 48 months, but had an excessive amount above 120 months. So what we did to decide if the model itself was flawed or if it was just suffering from a lack of data was we looked at the performance of our model compared to the state of the art and radiologists over the portions of the data set that we were selecting. So on the full data set, our model does do far worse in mean absolute error compared to radiologists and the state of the art models. But when selecting for the portion of the data set that we have the most information of, with people above 10 years of age in bone age, you can see that it does better than radiologists. And as we continue to move up the age, where we have even more data, you get better and better results that start to approach the state of the art while still using a very, very small portion of the data set. And so in summary, a unit with k-means ground truths can accurately segment X-ray images, and large data sets and expert annotations are not required for segmentation as in the past. This actually breaks one of the fundamental rules of machine learning, that a model is only as good as the data you give it, because we gave the unit purposely flawed data that does have very good aspects, and tried to see if the unit could generalize so well that it would take X-rays that had proper segmentations and take those features and apply to ones that even had ground truths that may have suffered through k-means. And we showed that neural networks can learn from imperfect data and produce desirable results. And in the future, we would like to train on a larger data set that has a more accurate distribution of the bone ages to see if the model does increase in accuracy, especially the SVR, and study the effect of the CNN and UNet structure on results, because we only employed a traditional UNet and a dense unit, while there are many other variations that are built for many other applications. And we also did not get the chance to compare our segmented images to that of the state-of-the-art model. And we also did not get the opportunity to apply bone age to its real-world applications, such as predicting height or in forensic science. And in the future, we could look at flagging bone ages that looks alarming compared to the chronological age of an individual. And in the future, we can also see how this UNet and this proposed structure performs on other types of data and other biomedical imaging problems, because in the past, image segmentation has been held back by its reliance on heavy data sets that are expensive and time taking to create, just to create one data set for one model. And so with that, I'd like to thank my mentors, Yao and Dr. Li Zhang, for all their invaluable mentorship over this summer. And I'd like to thank Dr. Boone for being the only person in this room with me approximately half of the summer, and Stephen Solomon for just setting everything up. And a special thank you to the UVMC Hillman Cancer Center Academy for giving me the opportunity to really learn and dive into the research aspect that I've never been in before this summer. So thank you.
Good job. Any questions? So Preetam, I have a question. I know there are very few images for younger children, but are the images of younger children, I know absolutely nothing about this, images of younger children a lower quality because of they're moving during the images, or is there anything else that could cause poorer prediction in the younger children versus the older children?
There's a lot of different distracting features, because I remember off the top of my head, one of the x-rays that we had to throw out actually had two baby hands on the same x-ray being held down by another pair of hands. So it just becomes an extremely distracting image, and unless you're trained to look for what you're looking at, it's extremely difficult. And there's also just not as many x-rays, because not as many children need to get an x-ray like at the age of like 3 years or 4 years. But the main problem with just the availability of the data and then the data that we do get is extremely complicated, because there's a lot more skin in like a 2-year-old's hand that can be more distracting, and their bones aren't fully developed and are just smaller. So like when you're looking at a normal hand, you can even feel your bones if you touch your arm. Well, if you take a baby's hand, there's a lot of distracting material that the x-ray reflects.
Awesome.
This is just a comment, but this would be very helpful when I send to a community hospital, sometimes I don't predict the image level. And so if this truly works, and it comes in smaller places like the medical hospital. The second thing is, like you said, younger children, mostly in general pediatric practice, we do bone age basically for height problems, short stature and stuff. So it's quite rare to get baby X-rays in general. So obviously that data set is not going to be as extensive to the huge.
Yeah,
It's a useful tool in small places.
one of the things we really wanted to look at is how can we streamline pediatric offices, because oftentimes they have to send things out to a ton of different places. But if you could just get a nice report with a bone age, maybe flagging it if it looks suspicious, and then a list of potential reasons why, that could be very beneficial to doctors. It could just help in their general practice.